take a look here. I'm going to go back over what I did yesterday real quick. So I'm kind of recording some of this. Probably won't pick up my voice, but at least pick up what it's drawing. Covalent compounds, bonds, and nomenclature. Covalent bonds are formed between two nonmetals. That's a key thing. So we're dealing with the right-hand side of your periodic table. Okay? For boron, carbon, nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, selenium, bromine, iodine. It also includes hydrogen because hydrogen is gas. We're dealing with nonmetals. We're also still looking at the valence electrons. Okay, valence electrons on top of your periodic table where we wrote VE. Okay, so we're still dealing with this, but in a different manner. We're not dealing with oxidation numbers or charges. That has no play. Okay. Now, Lewis dot structures is what we're going to be drawing. This is the main focus today. You'll get this. This doesn't take very long. Then we're going to start going into the naming process. I've got a couple of worksheets I'm going to give you to work on for the class, and I want to be able to go over that on Monday, make sure we know what we're doing. I'm not going to spend a lot of time on it. You will get the naming process pretty quick. It's not difficult. Then we're going to do some review on Monday, using Quizlet, Lab Tuesday, probably short test on Wednesday. Now, like yesterday, it looks like I got me off. Monday is not a 2-hour delay. There's no 2-hour delay. Okay. So, somebody told me that yesterday. I don't know if it was this period. I think it was third period, and that threw me off all day long. There is no 2-hour delay. Alright. Now, I think we kind of hit this yesterday. We have to look at the valence electrons. So we're going to draw the Lewis dot structure. So, hydrogen has one valence electron. Show that here. Now, this means they're unstable. Now, hydrogen can only have, they can only hold a maximum of 2 electrons. So if we have a hydrogen atom here, has 1 electron. Hydrogen atom here, 1 electron. Now, both of these are unstable. What's the maximum number of electrons that can be in the first energy level? 2. So, both of these are equal strength, so neither one is going to pull it from the other. So what they will do is they'll move closer together and share. So you're going to have a hydrogen atom here, a hydrogen atom here, and those 2 electrons will be shared between them. Next question. Can't be by itself. That is an unfinished. It needs the oxygen can't be by itself because it needs a complete outside energy level, so it's lacking magic number 8. Hydrogen, its magic number is 2, so it has to combine with something to get that. Now, if you take a look at oxygen, oxygen has 6 valence electrons. Each hydrogen has 1. Well, you have this here, this open spot here. Now, the electrons themselves are not going to be moved. It is the whole hydrogen atom that's going to move this one. So the hydrogen will move in position with the electron, and this is where you form a bond. Right? Now, yesterday, I had this here. It says a covalent bond is made up of 2 shared electrons. Now, there are 3 types of bonds. A single bond, where you have 2 electrons shared. A double bond, where you have 4 electrons that are shared. There's an error. Drawing. And a triple bond where you have 6 electrons shared. Triple bond here. Now, every atom wants to be stable. That's the key goal here. Okay? In order to become stable, they should form bonds. Now, to achieve a covalent bond, the electrons are shared. So keep that in mind, they have to be shared here. The magic number is 8, except for hydrogen. Hydrogen needs 2 electrons. Now, if you take a look here, and this works a little better, find this slide on paper. Like 2 hydrogens. Take a look at your periodic table. Okay. Now, hydrogen. How many valence electrons does hydrogen have? It has 1. So this one has 1. Good. Now, The other hydrogen also has one valence electron. Now, the position of these electrons does not matter around this. I had you draw it a certain way starting on the right, but it does not matter because these electrons are going to pair up, right? So they're actually going to move. Now, when we do this, we always count the number of electrons we start with. This hydrogen has one, this one has one, so we have a total of 2 electrons. All right? Now, what's going to happen is they're going to share. Those electrons are going to move between the 2 hydrogens. Now, yesterday I think I briefly mentioned about a Venn diagram. This is how that shows up. When we draw this, you're basically thinking of this as the atom. We're drawing the atom here. This is one. Here's the second atom. The 2 electrons in between are shared. Right? Now, that's not the way we draw this. It's a Lewis structure. When electrons are shared, we draw those 2 electrons as a dash. So that dash represents 2 electrons, and the dash stands for a bond. So we always draw it like this to show the bond. This is only done with electrons that are shared. Now we have 2 hydrogens involved, so the formula is H2. Right. Make sense to that part? Right. Let's go to the next slide. Here we have fluorine. How many valence electrons does fluorine have? Okay, 7. So this one has 7, and this one has 7. All right, let's take a look at this. Now for fluorine, and I'm going to draw it like this. I'm going to show my 7 valence electrons. And I'm going to put the single one on the right. That kind of makes things line up a little better. And for this one, I'm going to show my valence electrons. And I'm going to put the single one here. Now, when I draw it like this, it gives you an obvious avenue here to show the shared electrons. So we know that these 2 in between here, those are going to be shared. So when we draw this, the 2 that are shared, let's change that back a minute, are in between. And then we show this fluorine now has 8, correct? This one also has 8. So they both have that octet, so they're both satisfied, and they're both now stable. Now, my total valence electrons, I have 7 here, 7 there. That's going to give me a total of 14. The way we check to make sure we draw this right is to go back and check our electrons. I should have a total of 14. I have 2, 4, 6, 8, 10, 12, 14. Okay. Now, when we draw a proper Lewis structure, the pair of electrons that are shared will be represented by a dash. The electrons that are unpaired are still shown as dots. And I have 2 fluorine here, so what's my formula? F2. That's all we're doing here. So basically, we're identifying our valence electrons. We're showing how they are shared. We draw a proper Lewis structure, and we draw a formula. That's kind of what we're working on. Now, typically I stick to things that are fairly simple, single bonds. But on occasion, I may throw a double bond. Now, here we have oxygen. Oxygen can present a slight problem. How many valence electrons does oxygen have? It has 6. So each one of these has 6, so I'm going to have a total of 12 valence electrons.
What?
Now, take a look here. Oxygen has 6. I got 2 singles here. This oxygen also has 6. 2 pairs, 2 singles. Now you can see these 2 are going to be shared, right? Okay, so we know these are going to be shared. Here's 2 singles as well. Anytime you have a single, you know they're going to be shared. So these are going to be shared as well. Right? The ones that are shared must be in between. Right? So if I go to draw this, that are shared go in between. The other ones, I'm going to kind of spread them out a little bit. They can be rearranged. I'm going to move those to the outside. Now if I look here, this one has 8. And now this one has 8. The 4 that are shared are in between. Right? Now if I go back and count, I have 12 valence electrons. I have 2, 4, 6, 8, 10, 12. So I'm good. My electrons are counted. Now when I go to draw the Lewis structure, I have 2 pairs here that are shared, so that's going to be 2 bonds. That's referred to as a double bond. The unpaired electrons are shown here. Right, so if I go back and count, I have 2, 2 here, 2 here, 4, 6, 8, 12. Right. The formula for oxygen is O2, so now both of them are safe. Now, let's drop down here to another one. I rarely do this with you guys with double bonds, but it's going to be single bonds, so I'm not going to dwell on this a lot. Now let's drop down to the hydrogen and oxygen. Hydrogen has how many valence electrons?
1.
How many does oxygen have? 6. Now, odd numbers are not good. Okay, no problems. This is going to give us a total of 7. That's probably not going to work out the way we want. Now, hold on. Hydrogen has 1 valence electron. Oxygen has 6. Well, you can see this hydrogen is going to bond here, correct? So how can I remedy this? There you go. We're going to add another hydrogen here. So if we have it here, then that will give oxygen 8. So if I have another hydrogen here, 1, 2, that gives me a total of 8 valence electrons. Now if I go to draw this, I've got my oxygen, I have my unbonded pairs, and I have the ones that are shared here. Oxygen has 8, each hydrogen has 2. That makes all of them stable. This is water. Now the bonded pairs are shown as a dash. So it looks like this is the Lewis structure. Dash, dash. Now, we have H2O. Hydrogen. Yep, that's what water looks like. Water is actually a bent molecule. Follow the line here. Kind of makes a V shape. Okay, turn it around. So it's actually a bent molecule. Now, let's try carbon here. Carbon has how many valence electrons? 4. And we know hydrogen has 1. It's an odd number. Probably not going to work. We're going to have to make some adjustments here. So carbon has 4 valence electrons. Hydrogen has 1. How many more hydrogens do I need? Okay, you see an easy bond here. I'm going to have to add some more hydrogens here. And you can see the easy bonds here that form. And so carbon and you can see hydrogen is happy because it has 8 now. Each hydrogen is happy because it has 2. So we have now 8 valence electrons. Now, as a Lewis structure, showing the bonds, this. Now, the formula is CH4, which is methane. Remember I told you yesterday methane is used as a fuel? Well, it works as a fuel because it contains a lot of energy. It has 4 bonds. And when you break each of those bonds, it releases a lot of energy. So things that are used for fuel typically have carbon and hydrogen in them, first of all. And they also have multiple bonds. When bonds break, they release a lot of energy. You would have the same hydrogen and carbon, except it's in longer chains and more bonds. More bonds, more energy. Yep. Even longer bonds. All these are mixtures, by the way. Alright, now, let's try the next one here, nitrogen. Nitrogen has 5 valence electrons. Looks like this. Hydrogen, of course, 1 valence electron. Now you can see an easy bond here. How am I going to fix the rest of this stuff? I need 2 more hydrogen. Now, take a look here. See easy bonds that form here. When we go to draw this, nitrogen has the magic number 8. Hydrogen has 2. Oops. That last one. Tends to have water in it. And too much ethanol causes parts to deteriorate. Especially it depends on what your engine is on. The structure is going to look like that. The formula is in H3. Now, this is ammonia in H3. That's the common name for it. Now, as I said, we're not going to dwell too much on the drawing parts of this, but I do have a worksheet for it. I do want to get to the naming part today, though. All right, I want you to find this slide, please. Now, naming compound. We do this when these are non-metals. We're going to have to use a different naming system, not with the charges. Okay? So, this is going to describe, this is actually an easy naming system. We're going to look at the prefixes here. Now, prefix mono, 1. Now, the prefix we use for 2 is di. Right. Might help if I actually write 2. There we go. 3, 4, penta is 5, hexa 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Okay, now, you are going to have to know these. Now, on Monday, I'm going to have you put this on index card. All right? Now, let's go to this. The naming process is fairly simple. Let's go to the rules here. Now, the element farthest to the left on the periodic table is always listed first. So typically, hydrogen is going to be listed first whenever it appears. So the one that's to the left is always listed first. Now, here's a key thing. We never use mono on the first element. Okay, that is never used on the first element. The fact that you list the element means there's already one there. There's no reason to tell me that it has one. So we never use mono on the first element. First element's changed. This name is not changed. We don't change that first element. We don't change the ending. The second element, like we did with the other naming system, still ends in IDE. You have to change the second element to an IDE. Okay? Don't interrupt, please. Let me finish up here. All right, carbon. This is carbon, right? I only have one there. I don't use the prefix mono. So it's going to be carbon. Now the second one is oxygen. How am I going to change the ending here? It's not going to be oxygen. It's going to be what? Oxide. Now I have two of these. So what prefix am I going to use for two? Di. So it's going to be carbon dioxide. That is how we do that naming system. CO2 is carbon dioxide. Let's take a look here. We know we have one carbon, and I have two oxygens. So the name tells you the formula. Right? That's the purpose of the prefix. So when we use the term carbon dioxide, we know there are two oxygens. That's what that comes from. Now, let's try the next one here. It's N. Nitrogen. Now, okay, iodine's going to be named iodide. I'm going to use the prefix tri. And we do use the two I's. So it's triiodide. Now, let's get to the next one. Now, hold on. C is carbon, correct? Now, I only have one oxygen. So it's going to be mono. Now, here's a key thing when we deal with oxygen. Okay, I'm not going to call it monoxide. I'm going to shorten this. This only applies to oxygen. We're going to drop an O. So it's monoxide. Okay. So anytime we deal with oxide, we're going to drop the A or the O in the on a prefix. We don't drop either. Now, trioxide. Don't drop the I's. Now, let's try the next one. I have, what's P? Phosphorus, and I have two of those, right? So I'm going to do diphosphorus. And I have 4 fluorines. So I have 4, so I'm going to use tetra. I'm not going to call it fluorine, I'm going to call it what? Fluoride. Yep, blue. So diphosphorus tetrafluoride. It's not that hard, is it? It's using prefix. So it's a very easy name. So let's think about this one. It's going to be carbon what? Carbon. What's the prefix? Okay, 4 of them. So tetra. So that's carbon. Tetra. So carbon tetrafluoride. Next one, SO2. Sulfur what? Use that prefix, the number. So sulfur. Di. So it's sulfur dioxide. Now, N is nitrogen, right? How many do I have? 2. So what prefix am I going to use? Dinitrogen. And tetra. Dinitrogen. Tetrafluoride. That's prefixes. the last one here. What's the prefix for 4? Tetra. Nope. Tetraphosphorus. And we're going to drop the A. So, tetraphosphorus dicoxide. Now, the next part, I think, is writing formulas. Writing formulas is very easy. Now, let's take a look here. Here, dinitrogen. So how many nitrogens do I have?
2.
That's N2. Tetrafluoride. So how many fluorides? 4. Very easy, right? Now your prefixes, you don't have any trouble. Here I have sulfur. Now one of those. We don't use one as a subscript. But I have dichloride. So how many chlorides do I have? 2. Here, silicon. I only have one of those. But I have disulfide. So I has 2. Here I have dinitrogen. N2. Pentoxide. 5.